Here's a problem to think about that will lead us to a new approach for solving problems and for writing programs even. If you look at the numbers here, 6, 7, 3, and 1, how could you find a mathematical expression using all of these numbers and basic arithmetic operations like plus, minus, times, and divide that comes out to a result of 24? Or how could you be sure that there isn't such a combination? Assume that you're allowed to reuse the operators, but you're not allowed to reuse the numbers. So take a minute and think about what kind of approach you could use to that. Not what the answer is necessarily, because humans might be able to use intuition or guesses or things like that for answers, but what kind of approach could a computer take to try to find that expression to equal 24? Pause the video and think about it. So, since computers typically aren't able to mimic the kind of intuition that a person might use for something like this, understanding enough about the rules of mathematics to see what kinds of starts make sense for it and what kinds don't, then what a computer will often have to do for a problem like this is to just sort of comprehensively go through the possibilities. So really the problem is asking you to choose a number to go first, and then choose a mathematical operator to go after that, then choose a number to go second, and a mathematical operator to go after that. And these are a series of choices. And programs can be designed to handle those kinds of series of choices and to find the best one, but they typically have to get very comprehensive in trying all possibilities. And that's exactly what we could write a program to do. We could write a program that could try using 6 as the first number, and then maybe it tries the plus symbol after that, and it chooses some other number to be the second number, like 7, and it could choose plus all the way through, plus 3, plus 1. That wouldn't be large enough. So then it might try instead to do 6 plus 7 plus 3 times 1. And it could try all of the possibilities of these on downward until it's tried everything where 6 is the start in it. And then it might try using 7 as the first number, and 7 plus something, and so on. 7, eventually down here we would get to where we were 7 minus something. We would try where we were 7 times something, and it would go comprehensively through all of the combinations and then move on to maybe a 3. 3 plus things, 3 minus things, and eventually, I know that it could find a solution with 3 times things, because it turns out the solution for this is 3 times 6 plus 7 minus 1. Oop, forgot the 7. Plus 7 minus 1. So eventually, if it tried all of the possible combinations, it would find this. It might find it another way, such as 6 times 3 back here, or something like that. But it would have to try lots and lots of possibilities to find the solution. It's very, very difficult, if not impossible, to write iterative, meaning like for loops or while loops, solutions to a problem like this, where there are many, many possibilities and we have to make many, many choices about them. It can actually be very simple to write a recursive solution to something like this, because essentially what you're asking to do is to choose something and then decide what to do for the rest. So choose the first thing and choose the operator, and then decide what to do for the rest. And then keep the first thing and try a different operator and decide what to do for the rest. And so on and so on. Because essentially, if you've got the first part chosen, then, for instance, if we choose that 6 is going to be our first number, then we're just asking, well, what's the combination of 7, 3, and 1 that I want? And if you chose that 3 would be your second number, then you're asking what combination of 7 and 1 you want from there, and so on. These kinds of problems where we're trying lots of possibilities and where we're perhaps even having to go back and rethink a decision that was made before, such as choosing 6 for the first number. Maybe we don't find a solution down there. We see that we could, but maybe we didn't, and therefore we might have to go back and choose and try seeing if 7 is a good first number. For instance, with my arrangement here, I would eventually, after I tried all of the 6, 7, 3, 1 combinations, I would have to go back and try not having 7 as the second number, but having 3 instead, and then I could find a solution from there. So this kind of algorithm that's done recursively and making choices or trying possibilities and sort of going back and trying different options from where you chose before is sometimes referred to as a backtracking algorithm. This can be good for problems like these sorts of combinations and orderings of things. It can be good for solving mazes, as you'll see in the activity today. And it can be good for solving lots of different kinds of puzzles, crosswords, Sudoku, and various other things. The beauty of it is that if our recursive system is set up correctly, we don't actually have to keep track of what values have or have not been used in some big table or anything like that, like you might have to do for an iterative solution to handle something like this. What we do instead is we allow the recursive calls to try out possibilities, and if we return from one of those recursive calls without a successful result, then at whatever level we're at, we try a different possibility. And so you're going to see some situations like this throughout the course, but in particular today you'll see them as you work on the Recursion 2 parts B and C.